Okay, so in this video we are going to work on the problem of finding the velocity and acceleration of a disk that is rolling without slipping on a curved surface. So there are some intricacies that need to be incorporated when we solve a problem like this, and hence we have chosen this problem. Let me just quickly describe the problem and then we will start working on it. So essentially the problem says that there is a convex surface of variable radius of curvature, and there is a disk that is rolling without slipping. So there is a disk that is rolling without slipping on this convex surface, and at a given instant the radius of curvature of this path, so this is a fixed path, or this is a fixed surface, and the radius of curvature is capital R. So let's say that at this instant the center of the center of curvature of this path at this instant is C. Then the distance from C to this point, and let's denote this point by O prime. So O prime is the point on the ground where the disk is contacting the ground at that instant. Let's say that the center of the disk is Q, okay, and the disk has a radius of R. All right, so this is the motion that is happening. It is also mentioned that there is an arbitrary point P on the circumference of this disk, and at a given instant, or at this arbitrary instant, this point P is making an angle theta with respect to the line CO prime Q. So CO prime Q is the line that goes through the center of curvature of this convex surface at a given instant. It goes through O prime, which is the point of contact of the disk on the ground, and O prime is a point on the ground. It is not the point on the disk, it is a point on the ground. And then that same line goes through point Q. So all these three points, Q, O prime and C, are collinear, because clearly there is contact, and so the center of curvature of the surface and the center of the disk would be in line with the point of contact. Now the point P makes an angle theta with that line, and so you can imagine that if I extend it, let's say you have another instant here. So at a later instant, let's say the disk is here. At that point, what can happen is that, so this is again, it's still rolling without slipping. So let's say at that instant the center of curvature is this point C. The center of the disk Q is here. The point O prime is going to be this point. Again, it is the point O prime is the point on the ground, on this curved ground, where the disk is contacting, and then at that instant the point P would have moved here because there is rolling without slipping, and then the angle theta would be this angle, right? And note that the radius of curvature is continually changing, which means that the center of curvature itself can move. It wouldn't if this base surface was a circle, but it is not. So the base surface is a convex curve, and its radius of curvature can change, and so the center of curvature also changes. So this is how the motion is occurring. And another condition that is given is that the point O prime moves with a constant velocity v naught. So in other words, now we clarify here that O prime is a point on the ground. It is the instantaneous point of contact. Okay, so we shouldn't confuse the point O prime by the instantaneous center of this disk. The instantaneous center of the disk, let's denote that by M, is going to be located at the same point but on the disk. Okay, similarly the instantaneous center of the disk here is going to be shown is here as shown. So O prime is different from the instantaneous center of the disk. So O prime is not the instantaneous center of the disk, but geometrically O prime and M are at the same location. It's just that M is on the disk. By the way, the instantaneous center is being represented by M. So M is on the disk, O prime is on the ground, and it is given that as the motion happens, or as the rolling motion occurs, the velocity of O prime is going to be v naught, and that's a constant velocity. Okay, so the rolling takes place in such a way that O prime moves with a constant velocity, and clearly it is tangential to this curved surface at any instant. Now let us write down what we want to find out. So determine the velocity and acceleration of P in terms of V naught, small r, capital R, and theta. Okay. By the way, it is also given that there is a set of unit vectors that are given. So there is a unit vector ET, and there is another unit vector EN, and ET is tangential to the to this curve, and ET is normal to this curve, or sorry, EN is normal to this curve. So EN always points towards the center of curvature from the point O prime, so in that direction, and ET is always tangential to the curve. So we are essentially, so as the disk rolls without slipping, this is ET and this is EN, and I should probably indicate the velocity a little bit better. Velocity is, the velocity V0 is parallel to ET at any instant. Okay, so this is the setup, and of course so use ET, EN, and there should be a third unit vector, and because we are essentially using normal tangential, there needs to be a binormal unit vector which is going to be perpendicular to the page but pointing inwards. Because the convention is that the binormal is the cross product between the tangential unit vector and the normal unit vector. So if I curl my fingers of the right hand from the tangential to the normal unit vector, then the thumb of the right hand represents the direction of EB, and it forms a right-handed triad in normal tangential coordinate frame. So there are multiple ways to solve this problem. Again, this is a problem which relies on our understanding of the three-term relative velocity equation, which is the relative velocity equation in a moving frame or rotating frame, and it also uses the five-term acceleration equation, which gives the relative, which uses relative accelerations between 2 points, and the five-term acceleration is an expression in a rotating frame. So we are going to use those. But even while using those, there can be multiple ways to solve this problem, and we are going to start with one method, and then we are going to explore alternate methods. So our first goal is to find the velocity of the point P. So velocity of P. Okay, so if we consider the three-term velocity expression, which basically relates the velocity of a point with the velocity of another point, then there are a few things that we can do. First, we can say that, okay, we are going to express Vp in terms of Vm, because m is the instantaneous center and we know it has zero velocity. That is one way to do it. We could also say that I'm going to express Vp in terms of O prime, where O prime is not on the disk but rather it is on the base surface. So we can do that and write our equation. And when we say write our equation, I mean write the three-term velocity equation. And thirdly, we can express Vp in terms of Vq, where P and Q are on the same rigid body, and write the three-term velocity equation. So in the first and the third case, first case meaning where we express P in terms of m, and in the third case where we express P in terms of Q, in these two cases, the 2 points PQ and PM in the two cases, they're on the same rigid body. Okay. However, if we use the second scenario where we express P in terms of O prime, there P and O prime are not on the same rigid body. O prime is on the base surface, P is on the disk. So that difference is critical because depending on which of the 2 points you choose, it determines what angular velocity we should be using when we relate the velocities of these 2 points. So we start by writing P in terms of Q. So we'll say Vp is equal to Vq plus omega cross rho P with respect to Q plus omega P with respect to Q dot R. Okay, so this is the general relative velocity equation, which basically says that the velocity P is velocity of Q plus the rate at which the PQ vector is turning plus within the rotating frame what is the velocity of P with respect to Q. Now here the rotating frame of reference, since P and Q are on the same point, the rotating frame of reference, P and Q are on the same disk, on the same rigid body. So therefore we are already assuming that our rotating frame is fixed to the disk itself. So since P and Q are on the same rigid body, so let me just put a demarcation line here. Since P and Q are on the same rigid body, i.e. the disk, therefore number one, rho P with respect to Q dot R is equal to 0, and number two is omega is the absolute angular velocity of the rigid body, which in this case is the disk. And we also clarify that our rotating frame of reference is the disk. Okay, so our rotating frame of reference is the disk. Omega is the angular velocity of the disk, the absolute angular velocity of our disk, and rho dot P with respect to Q in the rotating frame is equal to 0. Okay, so let us identify the individual vectors. So what is VQ? So VQ is the velocity of the point Q. Now note that the point Q is such that it is collinear with the points C and O prime at any instant. Okay, so at this instant, for instance, we know that O prime is moving with a constant velocity V0 tangential to the curved surface. C is at rest, and so therefore the velocity of Q is going to be just a linear extrapolation, okay, because this whole line is turning, the whole line is turning about the point C at this instant. Okay, this whole line CQ is turning with an angular velocity of V0 divided by R. Okay, and if you also consider this point here, you see this whole line C O prime Q, that line is turning with a velocity of V0 divided by R. Of course, R is changing from time to time. Okay, so if this line C O prime Q is turning with an angular velocity of V0 divided by capital R, then what is the velocity of the point Q, knowing that the velocity of the point C is 0? Well, then the velocity of the point Q is V0 divided by capital R, which is the angular velocity of this line, times this whole distance, which is capital R plus small r. So essentially the velocity of Q is V0 divided by capital R times capital R plus small r, and it is going to be, because the line is turning about the point C, so all the velocities along CO prime M are parallel, and so therefore it is parallel to V0, and V0 is tangential to the curve, so therefore the velocity here is also tangential to the curve, and the direction tangential to the curve is the ET unit vector, so the unit vector is ET. Okay, so that's the velocity of the point Q. Now next we need to find the angular velocity omega. Now keep in mind that the omega is the angular velocity of the rotating frame, as we have written here. Omega is the absolute angular velocity of the rotating frame. In this case, the rotating frame is fixed, rotating reference frame is fixed to the rigid body. So omega is the angular velocity of the rigid body, that is the disk. So what is the rate at which this disk is turning? So we might be tempted to think that the disk is turning with an angular velocity of theta dot, but that's where this problem has got a uniqueness, in that it is not theta dot, because theta is being measured with respect to this line, right, CO prime Q. As you can see here, after a few instants, when the disk has this configuration, still the angle theta is being shown with respect to this line CO prime M or CO prime Q, which means that the angle theta is not an absolute rotation, it is a relative rotation. It is a relative rotation with respect to this line. So in terms of the angular velocity of the disk is not really theta dot, because theta dot only gives a relative angular velocity. It is theta dot plus however much the line itself has turned, okay, or what is the rate at which this line itself is turning. Okay, so the net angular velocity of the disk is composed of two different quantities. One is what is the rate at which the line is turning, CO prime Q, plus what is the rate at which theta is changing. So it is so now what is the rate at which the CO prime Q line is turning? Well, that is V0 divided by R. That is the angular velocity with which it is turning. And what is going to be the unit vector? It is turning in this direction, so the unit vector is in the EB direction, that is the binormal direction. That is one component. On top of that we have theta dot. Okay, and theta dot is also turning in this way, which is in the binormal direction, so EB, and so the total angular velocity is V0 divided by R plus theta dot EB. Okay, now note that if this was a flat surface instead of a curved surface, then the radius of curvature of that path would have been infinity, right? And if this was infinity, then this term would become equal to 0. And then the angular velocity of the disk would be equal to theta dot. Alright? And that is expected because when this surface is a flat surface and when the disk rolls without slipping on a flat surface, then this line, the line joining, well, there is no instantaneous center anymore, but the line joining Q and O prime, if you extend it, it always remains vertical because C is at infinite distance. And because of that, the angle theta is then with respect to a fixed direction. And hence the angular velocity is, for a flat surface, is actually equal to theta dot because it is being measured with respect to a fixed direction. In this case, it's not. In this case, this direction of CO prime Q is changing, right? And so we see that this is a more generalized formulation of the angular velocity of the disk, and the flat surface is a special case when r becomes, or r tends to infinity. Now, while we have this expression, we do not know what theta dot is, and we need to figure it out because it is clear that because the disk is rolling without slipping, so there is a definite expression for theta dot. It's not arbitrary, because if theta dot was arbitrary, it wouldn't guarantee that there is no slipping. So we need to figure out theta dot in terms of the other parameters here, such as V naught, capital R and small r, to figure out what is that expression, so that ensures that the disk is rolling without slipping. That is, the point M has zero velocity. All right. So let's find that out. Let's find what is theta dot. Now we can find out theta dot in two ways. One is just a visual inspection, and another is by direct use of this three-term velocity equation. So we will demonstrate both. If you just go by visual inspection, you can formulate theta dot in the following manner. You can say that, let me put another page here. So determine theta dot by visual inspection. And when I say visual inspection, it's not really entirely visual inspection. It is visual inspection and of course some reasoning. Now what we are saying in this approach is that let us consider the disk, and let us say that this is the instant of interest, this is center, this point is O prime on the surface, and this is Q. And here we have the point M, which is also which is coincident by O prime, but it is a point on the disk. Now, if the disk was not spinning and the disk was just sliding on the surface, what would have happened is that, so if disk was just sliding, not spinning, then the velocity Vm would be equal to, see, this is capital R this is small r, and O has a velocity like this, okay, and ET is here, EN is here, EB is into the page. So the velocity of M at that instant, if the disk was just sliding, the velocity of M would have been equal to V naught ET. Okay, it would have been the same as the velocity of O prime. Okay. However, we know that Vm is equal to 0 because there is rolling without sliding. Or rolling without slipping. So therefore, there must be another velocity here in the opposite direction that is cancelling this V naught. Okay, so there must be a velocity in this direction that is cancelling this V naught, causing M to be at rest. So what is that velocity? We say that velocity happens because of the spinning of the disk about the point Q. So let's say now the case where a disk is just spinning about its axis. Okay, so it is not moving, it is just spinning about this axis with Q fixed. So if disk was just spinning, then Vm would be equal to and let's say the point P is here, theta was here. If it is just spinning, then this direction is not changing. So this direction suddenly becomes a fixed direction if the disk is just spinning. So in that case, the velocity of the point M would have been theta dot times r, and it would have been still in the ET direction but with a negative sign. So it would have been negative theta dot r ET. So therefore, since Vm is equal to 0 when both sliding, or actually when rolling without slipping, when rolling without slipping. So we can say that rolling without slipping is a combination of slipping and spinning. Okay, the spinning action actually causes the slip between the two surfaces to become nullified. Okay, because this is true, therefore V naught ET minus theta dot r ET, so Vm is equal to this and this is equal to 0, meaning that theta dot r is equal to V naught, which means theta dot is equal to V naught divided by r. Okay, so that's a way to determine the angular velocity. We can also determine the angular velocity directly without the use of these intuitive means, but rather just formulating this problem in a structured manner. So we can say determine theta dot using velocity equation or relative velocity equation. And the way to do that is to say that Vm, which is the instantaneous center, is equal to Vq plus omega, so this is Vq plus omega cross rho m with respect to q plus rho dot m with respect to q in the rotating frame. Now note that again m and q, m is the instantaneous center and q is the center of the disk. M and q are on the same rigid body, and so this is equal to 0. When we write this equation, we are implicitly saying that our rotating frame is fixed to the disk. So the angular velocity is the absolute angular velocity of the disk. Okay, and in this case Vm is also equal to 0 because Vm is the velocity of the instantaneous center. Now we have the expression for Vq from the previous part, and we also have an expression for the angular velocity. So we can write Vq V0 divided by R, capital R, times capital R plus small r et plus omega. Now we have the expression for omega. Omega is V0 divided by R plus theta dot EB cross now m with respect to q. Now note that m with respect to q is a vector going from q towards m. It is going to have a magnitude of r and it is going to be in the direction of en. So magnitude of small r rather. So small r en. Okay. Now EB cross en, this is EB cross en, is is found by doing the cross product. So if we do EB cross en, we see that it is pointing in the direction of negative ET. So negative ET. So we have then V0 divided by capital R plus small r et minus r times V0 over capital R plus theta dot et. So from here we have V0 over capital R times capital R plus small r is equal to r times V0 over capital R plus theta dot. Okay. So we can say that r times theta dot is equal to, now let's take all the terms to the right and just keep the r theta dot on the left. So we have r V0 over capital R minus V0, or rather this should be minus because I have taken r theta dot and I am putting everything on the other side. This should be minus, this should be plus, plus r V0 over capital R. So these two terms cancel and we get theta dot equals this. So we see that we get the same result on the angular velocity if we use a formal approach to find it out. This is the relative angular velocity, which captures the the spinning motion. The spinning motion is such that it causes a rolling without slipping at the contact surface between the disk and the curved surface. So with this calculation now we are ready to move on to our overall velocity calculation. We note that in our velocity of point P we have we are trying to find out Vp. We have the expression for Vq, we have the expression for the angular velocity, and now this becomes V naught times 1 over capital R plus 1 over small r EB. Okay. So that is the angular velocity expression, and then rho p with respect to q is the vector that relates the location of p with respect to q. So you can see that rho p with respect to q is a vector going in this direction. So just to indicate it clearly, so rho p with respect to q is this vector. So we see that, and we need to express this vector in terms of using this triad. So we can see that since this angle is theta, see this angle is theta, so therefore r cosine theta is going to be in the negative en direction. R cosine theta goes in the negative en direction because en is pointing towards the center of curvature, and r sine theta points in the et. So we have r sine theta et sine theta et minus r cosine theta en. Okay. So now we can just plug in and say that therefore Vp is equal to Vq, so V naught divided by capital R times capital R plus small r et plus omega, which is this term, cross this, so plus V naught 1 over capital R plus 1 over r small r EB cross r sine theta et minus r cosine theta en. So EB cross ET, so if we do the cross products, we see that EB cross ET is in the EN direction, so EB cross ET is going to be the EN direction. So we will have let me actually go to a different page now to do the simplification. So therefore we have Vp is equal to V naught over capital R plus small r. EB cross ET is in the EN direction, so we have plus V naught times 1 over capital R plus 1 over small r times r sine theta En, and EB cross En is in the negative ET direction, so we have plus V naught 1 over r plus 1 over small r cosine theta Et. Okay, this minus became a plus because when we do EB cross En it gives us negative Et. Here we should put Et so we can now combine these two terms. So we have V0 times 1 plus R divided by capital R, and we can factor out the small r here, and then we will have V0 1 plus again small r divided by capital R cosine theta. This is going to be in the ET direction, and in the EN direction we are going to have again V0 factoring out this r from inside the parentheses. We have 1 plus small r over capital R sine theta En. So this is V0 1 plus small r over capital R 1 plus cosine theta Et plus V0 1 plus small r over capital R sine theta En. So that's our velocity Vp, and we can verify that indeed if the radius of curvature is infinity, which means when the surface becomes a flat surface, then the velocity expression is found by just putting small r over capital R to be equal to 0, and then what happens is that we get the velocity of the point P if the disk was rolling without slipping on a flat surface. So again, as we mentioned earlier, this can be considered as a more generalized case of a disk rolling on a horizontal surface. It is generalized in the sense that instead of assuming the surface to be horizontal or flat, we are assuming the surface to have a curvature and bringing the radius of curvature of that base surface itself into the picture, and in that sense the velocity expression that we get is a more generalized expression of the velocity of any point P on the disk as it is rolling without slipping on a general surface with a radius of curvature R. So we'll stop here. There are other aspects of this problem, like finding the acceleration, showing how this calculation is done using a different rotating frame of reference, and we will cover those in subsequent videos. Thank you so much.